with Mr. Einstein, okay? Along came Einstein. He had heard about the Michelson-Morley experiment. He said, I can explain it. I can explain not only what's going on, but the consequences of that. He began with two postulates. A postulate, Jaden, is a fancy word for I'm not going to prove this, I'm going to accept that this is true, and if it's true, I'm going to show you what else I can prove. His first postulate is that physics is the same throughout the universe. Now, he phrased it a bit differently. He said this: if two frames of reference, if two separate situations are moving at a constant velocity, if you're moving at a constant velocity, what's your acceleration? 0, relative to each other. The laws of physics will be the same in both frames of reference. In other words, let's suppose you're on an airplane, a jet, and you know the jet is moving at 700 kilometers per hour. As long as it's not accelerating, if you pour coffee, it'll go straight down into the cup. It'll behave just as though you pour coffee when you're at rest. Now, if you go around a corner in a car and you pour coffee, the water will slosh. That's different. He said, I'm not going to talk about acceleration. By the way, general relativity was when he asked himself, what if I let things accelerate? That took him 10 years of heavy-duty math. But for now, he said, if objects aren't accelerating, if you're going in a straight line at a steady speed, Dorian, if you're in a vehicle, no matter how fast it's going relative to me, as long as it's not accelerating, you and I will experience the same laws of physics. Okay? So I'm not going to prove that. That seems reasonable to me, based on what I've experienced. You can try this yourself, Jordan. If you're in a car and the car is going in a straight line at a steady speed, if you're in the back seat, you can play catch. Even though the car is moving forwards, when you throw something towards the person next to you, it doesn't go shooting backwards. It keeps going forwards with the car and ends up right on the lap of the person next to you. Is that okay? In fact, this was Mina, his first thought experiment. He said, I want you to imagine a car made of glass. If I throw a ball straight up and down, if I'm sitting in the car and I throw the ball straight up and down, as long as we're going at a steady velocity, the same thing will happen. But then he said, I'd like to compare what we see. Inside the car, this person playing catch would see the ball go straight up and land just beside him. What if you were standing on the road beside the car and the car is made of glass so you can see inside? Again, inside the car, the person would see the ball go up and then down. But because the car is also moving sideways, what would you see? I think we're going to sketch the path right here. I think you would see the ball go kind of like that, because it's moving sideways as well as up and down. Can you use your imagination? And does that, you agree with me, Jaden, if we use our imagination? Okay. This was Einstein's first leap. Although instead of a car, he said, let's imagine a spaceship so we can go even faster. Now, why is that nice? Because if I then do this, I can bring some trigonometry into the play. And you've done SOHCAHTOA and Pythagoras. I can bring some math in. With me so far, Conlon? Okay. So, the second postulate Einstein said is, he said, I agree with the Michelson-Morley experiment, because it was still debated. People still thought maybe they measured it wrong. He said, no, they didn't measure the speed of light wrong. You get the same answer for the speed of light. You'll measure the same speed of light no matter what the velocity of the observer's frame of reference is and no matter what the velocity of the source of light is. In other words, Kennedy, unlike the baseball, where you got a different answer if I was moving towards you or away from you and I threw it, for the speed of light, no matter how fast you and I are moving relative towards each other, and now let's think cosmic and think moving really fast, we'll still get the same answer. Or fancy word, the speed of light is a word that begins with the letter C. Constant. So his second postulate, he said, I'm going to agree with that experiment. And then he said, now watch. Here's what I can prove with some simple math. We're going to talk about time dilation. Little note. Dilate means make wider or longer. So when we talk about time dilation, we mean time is getting longer, it's slowing down. According to Einstein's theory of special relativity, a clock that is moving relative to something else will slow down. This stretching of time by a moving object is called time dilation. And then here is where Evan Einstein earned his street cred. He said, look, I'm going to do that ball experiment, but instead of using a ball, I'm going to use a beam of light, and I'm going to use that as my clock. I'm going to bounce a beam of light back and forth between a mirror. So here's his thought experiment. He said, I want you to imagine a spaceship made of glass so we can see inside of it. And the spaceship is going to go at a speed v really fast. It's going to go at a steady speed, no acceleration, because he said the laws of physics are the same for anybody not accelerating. And I'm going to bounce a beam of light, boom, 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 back and forth. Inside the spaceship, the person will see the beam of light going bump, 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 bump. But what would somebody outside the spaceship who saw the spaceship go zipping past see the beam of light do? That path there. Right? Same argument, just instead of a ball, beam of light. So, he said this, is it possible that in two different frame of references, identical clocks running on light might run differently and that time might pass differently? In fact, this is one of the predictions of Einstein's special theory of relativity. So, figure 15.6, I stole this from a different book, illustrates an observer inside an imaginary, custom-made glass-walled spaceship so that we can see in from the outside. And the inside observer is watching an event consisting of an imaginary, oscillating light beam. The oscillating light beam, turn the page, acts like a clock. Tick, 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 tick. Now, Mina, it's a really fast clock because light moves really, really fast, but it still acts like a clock. The beam goes up and down, up and down, up and down, up and down, up and down. It travels a distance. Now, the other thing we're going to use, and you can write this at the top of the page, we're going to use the fact that distance equals speed times time. You can write that at the top of the page there. Aaron, it's really d equals vit plus a half at squared, except I told you for his experiment we're not accelerating, so there's no a, so it's just d equals vt. Is that okay? All right. So here is his imaginary picture. I'm going to draw a line right there. That's a distance. Except instead of writing a distance, I'm going to write it as Vt. Which V? What's moving up and down? A beam of light. Who remembers what symbol we used for the speed of light? I mentioned it last day. What symbol do we use for the speed of light? Because light is a constant. C. So this distance right here would be c times t. We're going to call it t0, the original time on the spaceship. Okay? On the next page where it says DULP, you can draw a vertical line like that, and you can call it c times t0. That's a distance, that's how long it is, that's v times t. He also said the spaceship is going to be traveling forwards. The spaceship is traveling at a speed v for a time. That's a distance too. So on the next page where it says dulp, you can draw a second line like that, and you can call it VT. That's a distance as well. So on the next page over, right? It does say dulp there, I think, does it not? I hope, Jordan? Yeah. Okay. The third line he drew was this one. Now he said this is also the beam of light, but this is the beam of light that the person standing outside the ship sees. It's going to travel a distance c times t, but not with a 0. That t, that time, is different from the time on the spaceship, but that is still a distance. So where it says dulp, draw a hypotenuse and call that c times t, and we get a lovely right angle triangle. So now that we've drawn it, Josh, let me walk you through the argument again. So he said this figure illustrates a spaceship going by at speed v relative to the observer. So to the outside observer, the light beam in the spaceship takes a time t to travel. To the inside observer, it takes t0 to travel because time is different for both of them. And we get a lovely right angle triangle. Who remembers Pythagoras? What's Pythagoras' equation that you learn, I think in Math 8? It's got squares in it. Yeah. Up here, let's write a squared plus b squared equals c squared. Write that up there. We're going to do Pythagoras, Conlon, for this triangle that we have just dulped. Now, it's important to know, Bryce, this letter C is not the same as this letter C. We don't have enough letters in the English alphabet. But it's this squared plus this squared equals this squared. Ready? Bracket this squared plus this squared equals this squared. Now you gotta love Albert Einstein pulling Math 8 Pythagoras out to prove time dilation. We're not done yet. It says, step 2, isolate the CT0 squared. Get this by itself. Well, there's a plus VT squared. Hey, I can do this with you now. How would I move this over? Bryce, loud and proud. This is why I did that formula manipulation with you last class, last unit, because now any new topic, we can rewrite it, okay? So we're going to drop down the C, the T, the 0, and the squared, but the equal sign is going to be here now, and there's going to be a CT squared, and Bryce said we'll subtract the VT squared. Step 3 says distribute powers. I think you learn in Math 9 that if you have an exponent outside the brackets, which I do in all 3 of these, that you can put the exponent onto there, onto there, onto there, onto there, onto there, and onto there. Call it power to a power rule. In other words, I think we can write this as C squared T0 squared equals C squared T squared minus V squared T squared. Now what? Step 4, Einstein factored out the T squared. Good yawn? We're good? Hey, is there a T squared mechanism in this term here? Is there a T squared here? That's a GCF. I can factor it out. So on the left-hand side, the C squared and the T0 squared just drop down like a domino. Now I pause. Right around now is when kids' eyes start glazing over. Jordan, let me emphasize, I'm not going to ask you to redo this proof or anything like that. I'm purely doing this as a nerd, hoping you'll kind of follow the steps. So don't freak out if you're a bit lost right now. Equals, if we factor out a T squared, then we get C squared minus V squared left behind. Y'all got your green sheet handy? On the back of the page, near the bottom, about 2/3 of the way down, you have this weird equation with t's and t zeros. This is what we're trying to generate. And if you look at what we have so far, you can kind of see we're getting close-ish. Now what? What does step 5 say, Aaron? So look up. I'm going to go like this. Divide that by c squared. Divide this by c squared. Divide that by c squared. I've divided both sides by c squared. Or I could have just divided the t squared by c squared, but instead I put it inside the brackets already. Now why did I do that? Can you see? Can you see? 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 Sally, what? You're laughing, but what's the dumb joke? But what do you also see? Okay. Good. Those cancel? Yeah. And I get this. T0 equals t squared, bracket. Oh. Also, do you see? Here they don't cancel, but I have c squared divided by c squared. What's anything divided by itself? Okay, 1. And then there's a minus v squared over c squared. Yeah, we got to turn the page. Final step says what? Get the t by itself. I'm going to stay here. You all can just look up because we've done this. Ready? I don't want to get the t0 by itself. I want to get the t by itself. What's this bracket doing to the t mathematically? Adding, subtracting, multiplying, or dividing? Multiplying. So how will I move it over? Divide. So I'm going to get this. T0 squared all over 1 minus v squared over c squared. That equals t squared. Have we got the t by itself yet? Not quite. What do I have by itself? A t squared. Asia, how to get rid of a squared? You know this. Yeah, I knew you knew it. Okay, so on the right-hand side, if I square root the t squared, it vanishes. On the left-hand side, the squared vanishes, not the t. On the left-hand side, if I square root t0 squared, that squared also vanishes. On the bottom, it just ends up inside a great big uber square root. Now this looks ugly. I'm sorry, it's Einstein, Braden. There's a limit to how much I can tweak it. But this is the time dilation equation. It says this. T equals T0, sometimes pronounced T0, all over the square root of 1 minus v squared over c squared. You do not need to memorize this equation. This is the one that's on your green sheet, yes? What you will need to know is what each letter means, but we'll practice this. Where t is the time for the stationary object, the object that isn't moving, usually that'll be Earth, the time back home. T0 is the time on board the moving object, the spaceship, usually. Mr. Dewick, it would be nice if there was a dumb way that I could keep the T and the T0 straight. Well, there is, sort of. Tyla, what letter does the number 0 look like? O. I don't think of it as time 0. I think about it as, ready? time on board, O for on board the spaceship. Works for me. V is the speed of the moving object. Oh, and we already said what C stood for. What does C stand for? So this was Einstein's proof. And we're going to start to use this. Oh, we're going to do one more tweak. In this equation here, can you draw a little arrow pointing to the v squared over c squared? You may even perhaps do this on your green sheet too, but wait till I show you what we're going to do. I find it easier, this is how he wrote it, I find it easier to go v over c all squared. That's what you'll see me typically write, and you'll see why in a little bit. But v over c all squared is v squared over c squared, right, Zach? Okay. Let's crunch some numbers. You're going to want your calculator out. I'm going to skip example 1. I'm going to come back to it. I'm going to do example 2. Let's go on a spaceship. So it says this. Read along with me. A spaceship is traveling at 85% of the speed of light. If 1 year passes on the spaceship, how much time passes back on Earth? Let's imagine the spaceship goes away for 6 months and comes back for 6 months. There's our 1 year. Okay. Zach, can you read to me the phrase that tells me what we're being asked to find? Comes after the comma. Loud and proud, you're right. Read it again. Is that T or T0? T0 is on board the spaceship. T is the time back on the stationary object. Okay. This is Einstein. We're not going to take shortcuts. I'm going to defic with a vengeance. So I'm going to write down T equals question mark. Okay, Zach. How much time, what's T0? Time on board the spaceship. How much time elapses? 1 year. 1. Mina, you're not foolish on your phone right now or anything like that. That would be silly. The nice thing about Einstein's equations here, Jordan, is they are unitless. If you put in years, you'll get years out. If you put in seconds, you'll get seconds out. If you put in hours, you'll get hours out. If you put in days, you'll get days out. So, Tyler, we don't have to change our units if we don't want to. My earlier class, somebody, when I asked them how much time, 365 times 24. No, we don't need to go to seconds. 1 year. This will just give us an answer in years. Zach, how fast is the spaceship traveling? Can you read me the phrase that tells me that? I want you to read that again. You're right, loud and proud, every word.
85% of the speed of light.
I'm not doing this to make fun of you. I'm doing this to show you how my brain reads this. So read it again.
85%.
Stop. Read it again.
85%.
Stop. I stopped there. First of all, my brain goes back to math 8, and it says I'm not allowed to do math with a percentage. I can't use 85. What do I have to do with that? Change it to a decimal, right? So 85% is what as a decimal? Okay, hopefully that one you've learned by now to do in your head. So I'm going to write 0.85. Read me the phrase again, starting with the 85. Go again.
0.85.
No. Change it. Read me the exact phrase from the question again.
85%.
Stop. I've already done that change. Start over. Read it again.
85%.
You missed a word. Stop. So start again.
85%.
Stop after the word of. I'm serious. Many of you have never been told this, and it drives me crazy. I would teach you this back in grade 8 or grade 9. The word of is a math word. It means a specific mathematical operation. And if you knew that, it would make your life a lot easier. The word and is a math word. If I say to you, what's 5 and 6, what mathematical operation are you going to do? Add, right? Okay. Less than usually means subtract. Does anybody know what the word of almost always means? No. It means times. Put a little arrow pointing to the of and times. Whenever you see that, times. So even though you're going to say the word of, Zach, what's my brain going to think? Times. 85% times, continue. I have a symbol for the speed of light. That was a long explanation to get that, and we'll never go through that long explanation again. But when they give me the speed of light as a percentage, it's going to be the decimal version of times c. I want an equation that has a t and a t0 in it. There is one. It's the one right from the sheet. It says this. T equals t0 all over the square root of 1 minus v over c all squared. Zach, what am I going to put in for t0? For t0? No. For t0? Don't overcomplicate it.
1 year.
Just 1 over square root 1 minus bracket. Zach, what am I going to put in for v?
0.85. C. 0.85 C.
Ah! And then there's going to be a c down there, squared. Sally, do you see? You see? What do you see? That's why we did it this way, so that although the speed of light is originally in the equation, if I give you my speed as a percentage of light, the c's will cancel, which makes the equation nicer. In fact, what I get is this. 1 over big square root of 1 minus 0.85 squared. Get your calculators out. I strongly to the infinity power, strongly recommend that for this unit, you follow along each question and type with me, because this is heavy-duty typing. I don't know how all your calculators work. How many of you have the calculators that do a 2-line fraction display with a clear top and a clear bottom? Okay? You can type this in, Connor, a lot easier than we can. So do it your way, and if you get the same answer as us, smile a little superior smile because you're doing less typing than us, and know that you're right. For me, I start inside the square root. Zach, read to me what's inside the square root.
1 minus 0.85 squared.
I type 1 minus 0.85 squared, and I hit equals. That's inside the square root, yes? So I'm going to take the square root of that answer. I'm going to use my square root answer button. My calculator opens up a bracket. Yours may or may not, but all of you, because I've gone on my rant about calculators, hopefully by now have an answer button. I hit equals. So the whole bottom part worked out to 0.526. That's what this bottom thing worked out to. What's on the top? No, what's on the top? So 1 divided by that answer, the bottom part. That's how I do these. You may, with your calculator, find cleaner ways to get there. Mine, I just go step by step. I do what's inside the square root. I hit equals. I square root that, hit equals, and I go top divided by answer button because it's on the bottom. And I get 1.9. Yes? You got that too? By the way, the abbreviation for years is the lowercase a for annually. The reason is the letter Y is already taken by the US for yards. So if you ever go to like a bank and get a loan or something like that, you'll see they abbreviate your loan term with an A, not a Y. Annually is what it stands for. Now, here's what this means. This is not a math trick. This is not me being clever. It means that the astronaut comes back. So let's suppose this astronaut left in 2017. When they came back, their clock would say 2018, but nearly 2 years have gone by. The Earth would probably be in 2019. You have traveled into the future. 1 year has elapsed for the astronaut. Almost 2 years have elapsed back on Earth. Time travel is perfectly possible. It is. Let's kick it up a notch. Example 3. I think I said to you, Kennedy, during the last lesson that if we do ever invent space travel, if we do ever invent spaceships that can go near the speed of light, they will be one-way trips. They will be one-way trips because time is so different, is traveling so much slower for you on the spaceship that by the time you come back, everyone will probably have died. Let's look at an example. Suppose you're an astronaut and you're 30 years old and you've got a 5-year-old daughter, okay? You're going to leave on a space trip in the year 2000, just giving you nice round numbers, and you're going to travel at a speed of 0.99 c. What percent of the speed of light is that? Mina, loud and proud. Good. So let's suppose we have a spaceship that can go 99% of the speed of light. And you're going to go away, Mina, for 6 years as measured by you on your clock in your spaceship. So you're going to go 3 years out, 3 years back, 6 years. In other words, from the space traveler's frame of reference, T0, the time on board the spaceship, is going to be 6. How much time will have elapsed back on Earth when you return? How much time will have elapsed when you return from the frame of reference of your daughter? What does this question want me to find? Which T? T0 or T? You're gone for 6 years as far as no, that's what your space clock says. That's what all your watches say. You're traveling at 0.99 c, 99% of the speed of light, which is pretty fast. The time dilation equation says T equals T0 all over the square root of 1 minus V over C all squared. What's T0? The time on board. How much time elapses on board the spaceship? 6. Square root of, all over, square root of 1 minus bracket 0.99 c over c all squared. Do you see? Can you see? McKenna, you see? What do you see? Okay. Now, that only works if I give you the speed as a percentage of light. I will later on give you the speed in meters per second, and we'll actually need to type in some numbers there. But customarily, it's easier to do it as a percentage because of that. Here's what we end up with. 6 all over the square root of 1 minus 0.99 squared. I'm going to carefully type this in. You can try typing this in on your calculator. How much time has gone by back home on Earth, I get 42.5. Yeah? 42.5. Remember, the little a stands for years. Now, Braden, let's think about that. So here's what this means. You left the Earth in the year 2000. You arrive back on the Earth relative to the Earth in 2042. How old will your daughter be? How old was she when you left? Plus, how many years has she experienced back on the Earth? So your daughter is 47 and a half years old. How old are you? How old were you when you left the Earth? 30? How much time passed for you aboard the spaceship? How old are you? 13 years younger than your daughter. And this is not witchcraft or it's not a silly math trick. This is how the universe works. Interstellar explored some of this a couple of years ago, except in Interstellar, the time dilation was not caused by traveling at high speeds. It was caused by gravity distortion due to a black hole. That was Einstein's general relativity theory. That's the one that took him 10 years of heavy-duty math to prove. That's the one that the math is well beyond my mathematical ability. I've tried looking at it every so often. I get about 2 pages in, and I'm lost. But it has been proven by people far smarter than me. But this is why, hey, space travel will be a one-way trip. And that's a 6-year trip. There are a couple of stars that are within 5 or 6 light years. I think traveling at 99% of the speed of light for 6 years there and back, so 12 years, you could get to Proxima Centauri, and we do think there's a Goldilocks planet there, which might have water. We're not sure, but it's in the right area. But you'd be coming back, and everyone that you know, and just also think about the difference that Earth would go through in technology and history in 42 and a half years. If you go back 42 and a half years from us, you're in the late 70s, early 80s. How much has technology changed? How much has society changed? One more and we're going to pause. I know I've skipped example 1. Example 4. What if you want to travel into the future? Okay, so now we'll do the Back to the Future time travel. We're not going to use a DeLorean, we're going to use Einstein. Suppose a spaceship is traveling away from the Earth at 99.9% of the speed of light. Back home on Earth, 1,000 years go by. How much time goes by on the spaceship? What's this question asking us to find? Time? Yes. Which one? T0, time on board. Okay. All right. Then, what's T? 1,000. What's V? Zach, what's V? What's V? Of the speed of light, times c. Okay? By the way, don't forget that, otherwise your c won't cancel and you'll be freaking out. All right. Our time equation says this. T equals T0 all over the square root of 1 minus bracket V over C all squared. What did you say we want to get by itself, Mackenzie? Ready? See the t0? How would I get it by itself? What's this big square root thing doing to this t0? It's dividing. How will I move it over? Oh, are you telling me another equation, which I really don't need to put on my formula sheet? I can derive it. Times 0, I guess, is t times that big square root sucker? Mm-hmm. By the way, this is really why I emphasized the whole formula manipulation thing last unit. Way less memorizing. Okay, let's plug and chug. Times 0 equals 1,000 square root of 1 minus 0.999c over c all squared. Oh, I see. I'm going to type this by going 1 minus 0.999 squared, square root of that, and then 1,000, not divided by, but times that answer. How long would the spaceship need to travel for? You get 44.7? So if you went away for 22.35 years, turned around and came back for 22.35 years, that would be 44.7 years, and you would have traveled in your lifetime 1,000 years into the future of Earth. You would not notice any difference while you're traveling. You don't notice that time is slowed down because all of the time around you has slowed down. You can't tell. You can only tell when you meet up with someone else who is moving at a different speed relative to you and you compare clocks. It gets weirder. Are you kidding me? Oh yeah, but cooler. But we're going to pause here. Eventually, I'm going to assign to you every one of these questions, and I did attach the answers at the end. I will also put a handwritten answer key showing my steps online, because some of this is pretty heavy duty. But right now, you are already capable of doing 1, 2, 3, and 4. 1, 2, 3, and 4 don't involve any math. They're just asking you thought experiment questions to see if you've wrapped your brain around some of this stuff. You can skip. Oh no, we can do 6. You're capable of doing 7, 8, 9, 10, 11, 12, and 13. You do not have to have those done for tomorrow. We're going to finish this lesson tomorrow, next class. I'm going to give you time to work on the homework. But if you want to get a head start, because I'm giving you 10 minutes or so left in class to work on this, you can get a head start on this. Final comment. As you leave the class today, when you stand up, I will make certain to sit still. You can realize that as you are moving past me, moving relative to me, you are aging slightly slower than me sitting here, because time is moving slightly slower for you as it is for me. And that is true. Not by much, but it's true. Little nerd trivia.